Okay, another lecture on wavelets, by the way, today. Wavelets and what I call multi-resolution analysis. MRA is the sort of the standard abbreviation for that. So ultimately what we want to use wavelets for, or what a lot of people figured out very early on about wavelets is, look, this is a nice way to take large-scale structure, then take smaller scale structure, and smaller and smaller and smaller, okay? That is the power of wavelets. You take one signal, and essentially you just do different resolution levels on it. And you collect these different resolution levels in your wavelets that you constructed. So the idea is to construct everything with some wavelet basis that you've constructed that does the following. First, you can slide it or translate it, and second, you can scale it. Okay? Written in this way, you have some mother wavelet that you might define, and then you discretize it, and M and N relate to the fact that you can slide this thing around, scale the function so it's thin, wide, whatever you want to do. So you capture the scale that you would like. Okay? So the scaling factor is M, and you can see that the M here plays the role of scaling the X variable. Okay? So if these were sines, this would be like, could go like sine 2x, sine 4x, sine 8x, and so forth. In other words, higher harmonics or higher frequencies. And the N slides you around. That's your little window, you slide around. Okay? All right. One big piece of the pie is missing, and that is the following. We need to understand that if I take a function and I want to construct my signal from some wavelet basis, that I better have some kind of orthogonality properties of these wavelets. In other words, what I want to do is construct these so that the following holds. When I take the inner product of these wavelets bases, okay, one with M and N, one K and L, that this inner product, which you can calculate, just some integral over the domain of interest, that this has orthogonality properties, where these are the Dirac delta. Okay, so in other words, the delta Mn is equal to either 0 or 1. They're 1 if m is equal to n. Okay. Why is orthogonality important? Okay. Ultimately, this is what allows us to take a generic function or signal and expand it in a wavelet basis. Without this, we're kind of in trouble, actually. So let's do two simple examples to just show you where this idea comes from. Okay, so let's talk about orthogonality more generically. Perhaps you've been using this without realizing its full importance in the system or in an application. So for instance, let's take some function f of x that's even. And it lives in a domain 0 to L. Now, one of the things that we've done already is we've already said in the early parts is, hey, I can decompose this signal into, let's say, Fourier coefficients, right? So if you do a Fourier expansion of this thing, since it's an even function, you might say, let's do the following. I will expand in Fourier modes. It's even function. Cosines are perfectly fine for this then. And there you go. How do you determine the A of n? That is the question you ask. That's the important thing you need to do. You give me a function f of x, and I'm going to do a Fourier transform on it. The only thing left to do is calculate those A of n's. Now, what we did in the 4th lecture of this class is talked about that. We said, well, I could multiply, for instance, everything by cosine m pi x over L. I don't need a little thing here. And integrate over my domain. What did we say about these two quantities here? Fourth lecture, if you look back at the notes, you can calculate what this integral is of 2 cosines. And what we made the comment was that cosine m pi x over L is orthogonal to cosine m pi x over L. In other words, this always yields 0 if n is not equal to m. But if n is equal to m, it equals 1 over L. Okay? So that is the idea. We're going to use this concept that if I take 2 of these functions, that this is equal to 0 if n is not equal to m, and 1 if n is equal to, 1 over L. So we use the idea of orthogonality directly in our Fourier expansion. Okay? And in fact, when we construct this solution in Fourier domains, we always think about all the Fourier expansion bases are all orthogonal to each other. That's how we can get away with saying, if I take a signal or a function and I expand it in Fourier basis, basically, as I take more and more Fourier modes, I converge exactly to the signal. Okay? We need that mathematical framework, or otherwise you just say I can expand something and it doesn't mean anything. You have to be able to have this as a footing, because now when you do this, this is 0 for everything. You're summing over n, except for when n is equal to m. And when n is equal to m, this is 1 over L. So this becomes a of m over L. Okay? So then you can solve for, or actually, yeah, anyway, I might have it upside down, but who cares? Right now, let's just go with it. Pretend I'm right. I wish my wife would do that more, but somehow she's lost credibility in pretending. She's a realist. And here you can solve for a of m is equal to, I think this is actually not, I think this is L, not 1 over L. And then a of m becomes 1 over L, f of x, cosine m by x over L dx, 0 to L. You can solve for all the coefficients, making up this expansion. So now when you say, I'm going to represent this signal in terms of cosine bases, there's one unique way to do it, and I can calculate all the coefficients. Okay? And I used orthogonality to do it. Okay? All right. Second example of the power of orthogonality comes from solving generic, non-homogeneous, let's say, some PDE, some ODE. You can ask the following question. I want to solve this problem here, let's say, where L is a linear operator. And let's say that it's self-adjoint. So this is basically a differential equation in some sense. It's linear, and let's say that L is, self-adjoint. So for instance, this could be something like, here's an example. Two derivatives in x plus some function of v of x. Okay. So generic kind of example. So how would I solve this, or solve it in terms of, let's say, doing an eigenfunction expansion way to solve this, which is one of the standard ways to do this, which is to say, consider the associated problem, this one here. Suppose I just forget the f of x for a moment. This is what makes the problem actually kind of hard. If you have some f of x in there, the non-homogeneous case is difficult to solve. But suppose you can actually write down the eigenvalues for the operator L. Then you could say, I'm going to do the following. Why don't I take my solution, u, and expand it in terms of these eigenfunctions? So this is called an eigenfunction expansion technique. So the idea is you just say, okay, so I've found this eigenvalue problem associated with L. Now I'll take the u and assume it's of this form, plug it in there. So then I have u this. Since L is a linear operator, I can bring it into this sum, and I have A of n, LUN equals F. And now what I'm going to do to both sides is multiply by U of M. Okay? So if I multiply by U of M and integrate, what I end up getting this is the generic way to write it. That's the inner product or an integral between U of n and U of m. And now I rely on orthogonality, which is U of n and U of m satisfy the orthogonality condition. This is why orthogonality is so important. So this thing here is either 0 or 1. It's 0 if n is not equal to m, and it's 1 if n is equal to m. So what does it say for here? Oh, sorry, I have to do one thing first. I'm going to move the L over, well, okay. So I'm going to move the L to the other side, or just do it here. This LUN gives me lambda n, A of n, U of n, U of m. Then I ask U of n, U of m. It's always 0 unless n is equal to m. Then it's 1. Okay, so I do this infinite sum, and it's always 0 except for at one spot, when n is equal to m. And then what's left over here is A of m, lambda m. I've just solved for my A of m, divided through by lambda n. And so when I write down my solution now, I have U is equal to the sum of inner product U of n over lambda n un. There it is. By the way, a couple things that I'm sweeping a little bit under the rug here is the idea of completeness. Okay? So typically, when you have in a self-adjoint problem, if you find the eigenvalues, eigenfunctions, you have what's called completeness in the system here and also over here. And what completeness means is if I take an infinite sum of these eigenfunctions or expansion bases, I converge to the solution, point by point. Okay? So you need this. What it tells you is that you can exactly reproduce f of x in the limit as n goes to infinity. Now, in computation, we're always going to cut this off, right? We're always going to say, I'll do the sum to a finite value. I'm not going to do an infinite number. I'm on a computer, right? I mean, I've got to actually cut it off somehow. So for instance, in our dog problem, you're doing 64 modes. You're doing 64 of these essentially in some sense, okay? So you always cut it off at a finite value, but the idea is you know that if you do more and more and more, you're going to converge exactly to this thing, okay? And the way you calculate everything all relies on orthogonality. So we need the same kind of concepts here, which is we still need this idea of I give you some f of x, which can represent a signal. What I got to be able to do is tell you, by the way, you can take that signal and represent it as a sum of wavelets. That's what we want to do. Otherwise, right now, this technique's worthless, except, hey, I have these things that slide around and scale. So what? You need to reconstruct the signal, okay? Everybody go with this? So orthogonality plays that really key role. And so we need that piece to do our next bit here with wavelets. Essentially, wavelets are just a different expansion basis, but we still haven't sort of shown the orthogonality property. And once we show that, then we can say, oh, it's just another basis. They have orthogonality, completeness, expand, any function you want in them. Okay, so a wavelet, phi, is orthonormal if the family of wavelets phi m, sine m, are orthogonal. Okay? That's the idea here. Now, by the way, this statement, orthogonal, is just simply reflected here mathematically. So my idea, no, not my idea, your idea, the idea. Let's call it the idea, no ownership. The idea here, right, is to say, look, we're going to make up some wavelets. And in wavelets, there's all kinds of wavelets you can make up. But what you really want to do in constructing the wavelet is make sure that when you construct it, these orthogonalities satisfied. Because once you have this orthogonality condition satisfied, and we talked about what the admissible condition for the wavelet was on Friday afternoon, then if you have this orthogonal basis, you give me some function or signal then I have this statement here. Take this thing, I can expand it in terms of my wavelet basis functions that are all orthogonal, where the coefficients are given by this inner product. This comes from orthogonality conditions. And this double series converges to F in the L2 norm. So if you do this series, it will converge to this, period. We have to have this in place to go further. Because our whole idea is going to say, give me signal, give me something I want to analyze, do a multi-resolution analysis on. And fundamentally, without this, you say, okay, yeah, I expand in these things. But unless you know that this thing that you're expanding in actually converges to your signal of interest, it's worthless. Now you have it. Now you can say, just like the Fourier expansion, just like any eigenfunction expansion method, you say, this is just a sum of a bunch of these wavelets, where I can calculate these things through orthogonality. Done. We can proceed. So there's this confidence level that you have. Do you feel more confident? You should. Because now it kind of justifies what you do, or what we're going to do. Okay? All right. So confidence aside, we'll continue on. Now we'll just keep going. Many of you are confident anyway, because you thought, hey, he's teaching, it must work. So I'll let him be confident for me. So thank you for having that trust in me. I appreciate it. All right, here we go. But now you can have trust in yourself. Or maybe not. But that's what you stand on for everything else from now on. Okay. Still not quite done. The way I see today's lecture is putting down some more of the mathematical framework. Hardly any pictures I'll draw on the board today, which is probably sad. You probably like to see my art and my little filters and things like that. None today. But the mathematical framework we put down is important because it kind of is going to close everything off together, have the pieces in place. And by the way, I am just giving you the very skimming off of what you can get very deep on the analysis very quickly with wavelets, okay? And I'm just kind of skimming off what I like to say is the good stuff, giving you the concepts, and then what we're going to do on Friday, since there's no class Wednesday, right? There's double up Friday again. Friday morning, I won't be here Wednesday, so Friday afternoon 4, we'll have the second lecture from Wednesday. But what I'll do Friday morning is I'm going to pop up my laptop here, and I'm going to show you what we're going to do with wavelets, which is you just basically, there's tons of software out there. You just take your signal. It'll do all the work for you. You want different wavelet bases, you just drag it down from a selection menu. Say, do it in this basis, do it in this basis. Analyze my data this way, filter it that way. All that stuff is there. Okay? It's kind of like a little bit like if you ever use finite element methods for solving equations, you typically go to some kind of packaged software, unless you really love to hurt yourself. Okay, so we're going to assume that you like yourself, and we'll go from there. And we'll start using, at least in this context, MATLAB toolboxes, but then I'll also point you to some other toolboxes that are out there for free. But I think a lot of you will have access on campus to the MATLAB toolboxes. So we'll talk about more of that later. Okay, so putting things on more theoretical footing again. So now we're going to talk about the concept of multi-resolution analysis. As the name implies, the This means we're going to look at signals or some kind of information at different levels of resolution. So, you know, when wavelets first came out, it wasn't like people thought, hey, this is exactly the application. This grew out as a clear consequence. It became very clear very early on that wavelets became a very natural way to think about things. Originally, there was this idea of thinking about, well, we want to think about time, frequency, domain issues. And that's still valid. And this still gives you time and frequency localization. But it very quickly became something bigger than that, which is to say, any problem with very big, you know, separation in scales, let's say in time. Okay, suppose I have a data set as an instance. I have a data set where I'm measuring, suppose I had this. I have 1,000 years worth of geological data. Okay? And on the big scale is how things changed over the centuries. Okay? And then, you know, maybe there's things that changed over the decade. It's a big scale separation there. And then you have, for instance, suppose it's some kind of temperature data. I can go all the way down to I have changes over the day or the year, right? So I have the seasons, I have the daily changes. All these are very different frequencies where they're all in this big data set. And the multi-resolution analysis just says, first let's pull out the millennial data. What are the big trends on the millennium? What are the trends on the centuries? What are the trends on the decades? What are the trends on, you know, the years, the days, the minutes, the seconds, the nanoseconds? You probably don't have your measurements every nanosecond, but maybe, Brian, do you have a nanosecond scale? Not yet? Okay. Okay, if you can get that, that's a PhD right there. Nanosecond temperature fluctuations in like the Puget Sound or something. Okay. Okay. So this is what it does. That's the totally contrived example. But you understand that if you try to analyze this data all within one framework of one Fourier basis expansion, the scales are so hugely different that you do a bad job on this. So this is a really nice framework for it. Okay. But more than that, this concept of multi-resolution analysis, what it gives us is an algorithm. Right? For constructing these different resolutions. Okay? So ultimately, that's what we're after here. It's a computational course. The idea is, yeah, here's some theory, and you can work around the equations all you want all day, but you're going to give me data. You're going to take data, and you got to do something with it. Okay? So there has to be an algorithm. We now have a footing to say we know that this multi-resolution analysis is going to work because we know that we can do this expansion in wavelet basis. It's going to converge. So now what we need is an algorithm that's going to tell us how this thing goes. Okay? So the idea is going to be the following. Consider a sequence of subspaces. Call them V of M, where M is part of the some integer values. Okay, so that's just okay. And these are going to be a sequence of embedded subspaces in L2. So with some space of real numbers. And what we're going to do is consider this. Consider these subspaces. And essentially what the subspace idea is going to be is we're going to take a subspace of large-scale structure, then subspaces of finer and finer and finer and finer scale structure. Okay? And what we want to do is separate out the scalings. Take your millennia data, take it out of the picture. Now let's go and look at what happens on the century data. That's another level of resolution. Decadal data, another level of resolution. Day-by-day data, another level of resolution. Okay? What we're going to do is confine each one of these levels of resolution to different subspaces. Okay? All right. So here are the properties of, or the definition of a multi-resolution analysis. First, we consider these subspaces as the following properties. First, that there is a sequence of subspaces containing the previous levels. Okay? So we're going to basically subset this down. So you have the big subset, and then you have smaller subsets where the data lives for the different resolution levels. Okay? A couple other important facts, too. The union over all the real numbers of the subspace, okay, is dense in L2. What does this mean? Well, this means if you take all these levels of resolution, you fill out the whole L2 space. Okay, so this is just an idea of completeness or convergence. In other words, it doesn't mean that I have information at all points in L2 space. It just means that there's no space in L2 where my subspaces cannot reach in some sense. Okay, so this goes to the idea of if I expand this basis, it's not like, well, you can get all the space except there's this special functions over here that don't do it. No, it just gets the whole thing. Okay, so that's ultimately what that means. All levels of resolution combined give you the full thing. Okay. Third property, the intersection of all these subspaces is the null set. In other words, there's an orthogonality between subspaces. Once I've taken out a set of data, no longer is in my picture anymore. I've extracted into one subspace that has some resolution. What's left is stuff that, let's say, for instance, is finer scale. So I've already taken this out. This no longer exists at the lower subscales, let's say. Okay? Property number 4. F of x is in V of m if and only if f of 2x is in V of m plus 1. So V of m is a scale resolution. V of m plus 1, what we think about V of m plus 1 is one finer level of resolution. In other words, you cut your resolution down by a factor of 2. That's the typical way to scale these things. By the way, over here, that's me dragging the cameras over. Did you see that? So I'm so fast, though. Did you see how fast I moved over? Anyway, all right, here we go. The factor of 2 is the standard thing. You rescale. Here's your scaling. Okay, this rescaling here goes like 2 to the nth power. Okay, so every time what you do is you start with something that's size 1, cut it into 2, cut it to 4, cut it to 8, cut it to 16. That's what you're doing. Every time you go down one level of resolution, that's what you do. You cut your, one way you think about it is you cut your domain in half, as it were, get the time resolution, cut each one in half, keep one in half, all the way down. So that's where the factor of 2 comes in. So when we come back over here, if f of x is in V of m, in other words, I've extracted this information at this level, at the V of mth level, okay? It's in there if and only if you took this information and you scaled it down 1. So like suppose this was cosine x, cosine 2x. This is a higher frequency component, more finely resolved component. That's in V of m plus 1. Okay? So this is a very important thing because it tells you how you go from one level of resolution down one step in the resolution. Okay? I'll say another comment about that in a minute. 5, there exists a scaling function phi in V naught. This is nice because I don't have to write very much. So there exists this phi in V naught such that I can think of this scaling function like this. Has some kind of shift to it, that this is an orthogonal basis for V naught, so that, okay, so it's orthogonal basis. Unfortunately, writing these property down is all kinds of words. I don't like to write a lot on the board. I like to write equations, but like sentences are, that's a lot of writing. In phi, it's called a scaling function. Or sometimes it's called the father wavelet. Okay, there we go. So ultimately what we're going to have is two kind of functions. We're going to have a scaling function, and then we're going to have these wavelet functions, which we're going to have mother wavelets, father wavelets, and all the beautiful children. Okay? All right. So, but we'll talk about, so the question is, what is the relationship between the father and the mother wavelet? Depends on what kind of, I better not even make jokes there. Okay. We'll just leave it at that. I'm so tempted. Okay, so there you go. So we'll discover that relationship in a moment. But these are basically the properties, standard definitions of what a multi-resolution analysis is. Multi-resolution analysis puts everything in terms of subsets of resolutions. Okay? All right. Now, what can we do with this? Whole bunch of stuff? That's the answer, if you were wondering. We can do a whole bunch of stuff. Okay. So what kind of stuff can you do? Well, let me first. Yeah, I probably put that in. Okay. One more comment then on, by the way, this relationship between going from V of m to V of m plus 1. So we normally start thinking about V of naught. A V of naught is your, let's call it, that's where your mother and your father wavelet live. Okay? Now ahead of time, you don't necessarily know what that scale is. So for instance, suppose you actually do a problem and you don't know how fine or how big the scales are. The nice thing about the wavelet analysis or the multi-resolution analysis, you give me a V naught. Suppose my V naught is I'm going to resolve things at a meter. Right? Well, what happens here in this scaling, so if that's V naught sort of a meter, then I can go down. Here, I can go down from meters down to microns to things like that. Nanometers all the way down. But I can also go up. I can go from meters to kilometers to, big things. All right, terakilometers. Meters. You don't put telekilometers. That's probably not good English. Okay. It doesn't matter what you start with. In other words, you don't have to start on the biggest scale. You don't have to even know what it is ahead of time. You can just start on your scale that you want, construct your mother-father wavelet scaling function and wavelet basis, and you can go up in resolution, down in resolution. Okay? It just gives you that freedom. All right. So, but here's one thing to note. And we have some scaling function psi, which is the father wavelet or scaling function for V naught. Then for V1, it's also for V1 in the following sense. Oh, sorry. So this tells us how we can scale from one to the other, essentially. And by the way, if I rewrite this with the thing I erased over there, in other words, this is translation and scaling. The baselet here is phi 0, 0, let's say. That's in the phi naught for V naught is this. But now, if you write this psi in terms of what would be the scaling basis, scaling function for V1, you get this, which is something like square root 2 Cn psi 2x minus n. Okay? So you get this shifting. And this is important because it tells you how something that fundamentally has a x dependence relates to something that has a 2x dependence. Okay? This is called the dilation equation. Okay? Or the two-scale equation. or the refinement equation, or the too many names equation. I made that one up. Right. Notice everybody's looking down. Okay. So there you go. It's got all these names, but it tells you how you go from one scale to the next in the scaling variable and how they relate to each other. Okay? All right. So now let's keep the construction going on our wavelet basis. All right. Here's what we want to do next. Generically, we have this. Nth level, the relationship between the nth level subset and the n+1 level subset. And one contains the other. And essentially what we can do is say, well, you know what? Vn+1 is actually we're going to define a quantity, Wm, which is the complement, orthogonal complement of V of n. So we have this space, V of n plus 1, okay? And V of n is in that space. But what's left over? Right? V of n is only part of that space of V of n plus 1. Well, what's left over, we call it W of m. And we say that this is the orthogonal complement of this. So these two together make up the space. These two are orthogonal to each other. Okay? All right. So that's how we think about getting from one to the other. All right? So, by the way, we can continue this. What makes up V of n? Well, that's actually V of n minus 1 with its, sorry, I got to keep drawing this right, with its orthogonal complement. Right? It's made up of a space V of n minus 1 and its orthogonal complement. And you can keep going, right? Then you can take what's in V of n minus 1? Well, it's V of n minus 2 and its orthogonal complement, W of n minus 2. Okay? You can keep all the way going down to V of n plus 1 is equal to V of naught with the orthogonal complement of basically all those guys together. Okay? Here's what's important about this. So where am I going with all this? Where I'm going with all this is that as n goes to infinity, this thing goes to, instead of this, and by the way, you can go back up too, right? So this is going one direction. You could go the other way, right? What's made up of V of n plus 1? Well, it's contained within V of n plus 2, right? So you go the other way. And so ultimately what you get is this thing becomes you sum up over all subspaces from negative n to infinity. And here's the idea. This spans the L2 space. Okay? So this is important. This is kind of the completeness argument. Okay? The completeness argument says, look, when I consider these subspaces, and I consider all the subspaces together, boom, the whole subspace. Yeah?
On the second line up from the bottom, to go from n equals 0 to n.
What's that?
Second line from the bottom.
This one?
Yeah, that n equals 0 up to n.
Yeah, 0 to m. And by the way, my notes will come out soon. So have no fear. It'll probably be wrong there too. No, it's going to be mostly right, but you know, I'd appreciate the help if you see like stupid stuff. That'd be awesome. Okay. All right. Moreover, not only does it span all of the L2, why do I need to do this, by the way? It seems like I'm just like making little tricks for you, like juggling. Okay, I'm a super awesome juggler. Look at that. I juggled all these V of M's and W of M's without dropping a single one. The reason I actually did this, and here's the important thing, you have to do this because now you get to the connection between the scaling function, or the father wavelet, and the wavelet itself, the mother wavelet. Psi versus, phi, which we have defined over here, which we say when we do a multi-resolution, there exists this phi, right, that it can do some things with, a scaling function. What is the relationship between that phi And what we've been talking about is expanding everything in size, which are the wavelet functions. Well, now you get that. So essentially, what the wavelet basis does, so once I have this, essentially what you can use is this idea to say that all these subspaces, orthogonal subspaces of WM, span L2, and there exists a function, psi, which is contained in omega, W naught. Remember, this is our mother wavelet. Okay? Remember, W naught, V naught. That's the space we started with where we construct phi, which is the father. And this is also where we construct psi, which is the mother. Okay? One is called the scaling function, or father. One's called the wavelet itself, and that's the mother. Okay? And we can construct this thing, and it constitutes an orthogonal basis. Phi mn of x is equal to 2m2. There. This is the orthogonal basis for that. Okay. Now, you may think, hey, I got a little technical in class today. Fine. Go read a book on this, and you'll see I actually, I think, did a pretty good job at skimming off, you know, the misery of most of what would go on in this. But it gives you, hopefully, the big idea. And once you have this, I'm going to write down one theorem. And this theorem is going to hold everything together. It's what we're establishing today, ultimately, is the following two facts. One, I can take a function or signal or representation, and I can expand it in terms of wavelets. This thing converges, and it's orthogonal. It's just like doing any other expansion basis that I want. That's one. Two, I've also established in some sense, ultimately here, the completeness idea, which is, okay, once I have all these bases, that if I do enough of them, it really does converge to that function in the L2 sense. And now I have a connection formula also between the scaling function itself and the wavelet function, which is the following. And let me write down this theorem. This is the primary reason we did all this background. If okay. If there is a multi-resolution analysis with subsets V of n with the scaling function phi, there exists a mother wavelet let me write this right. Here it is, -1. That can be constructed like this. Let me just write down there where the C of n Okay, so if we have this multi-resolution analysis with some scaling function phi, there exists a mother wavelet, and here's the relationship between the mother wavelet and the scaling function directly. And what it tells you, essentially, is how psi of x relates to phi of 2x, okay, where the C of n are calculated from some inner product. And this theorem basically says, look, if I have the multi-resolution, then I'm going to get something that exists that I can do this with. That's the big thing. So there exists an expansion I can use. I already know with orthogonality, I can expand any function now, and I have completeness. You're ready. So when you apply the wavelet analysis with a given wavelet basis function, you're done. It's going to converge to the signal. You can do it. You can do this whole multi-resolution analysis. Okay? So what's left to do? This is sort of technical format. The last piece then is to say, I still haven't really told you, we've just made up these very generic phi and psi. The one beauty about the Fourier transform is that the Fourier transform is defined as one specific function that you're working with, right? E to the I omega nm x or t, right? It's an oscillatory function. Here's the game you play now at this point. Once you set up this framework mathematically, and by the way, like I said, you can go to the library, stacks and stacks and stacks of books on wavelets. And what do people do with wavelets at this point? Well, what they do is, let's play some games. I got all this mathematical structure. We saw last lecture that if you have a wavelet, to get another wavelet, all I got to do is multiply by any integrable function, and I get another wavelet. So you can construct almost any wavelet you want, right? So what do you need to do? Well, what you need to do now is play games. What do you want? That's the question you ask. I want really good localization in time and frequency. Okay, let me try to construct you a wavelet basis that does that. Maybe you want something else, okay? So depending upon your specific application, what your job is to do is figure out what I should be building here to get me the most information for whatever your application is. There's ambiguity here, right? People don't like this. It's not like I can just say, hey, here's a code, wavelet expansion. You actually got to like think about what wavelets do I want, blah, blah, blah. So what we'll see on Friday is when I pull the computer up, there's a little drop-down menu. There's like 6 or 7 different wavelet bases you can use. And they're kind of just the standard ones, right? So you can imagine you can construct a lot of other ones as well. But we'll start playing around with that, and you'll start seeing how they work. Probably the most famous one we'll talk about. And by the way, also here's something nice about Fourier transforms. It's very easy to imagine cosines and sines, right? I expand in cosines and sines. It's a simple picture in your head about what these things look like. You have let's call it an intuition about how things should look like. Now, the ones we're going to talk about mostly, it's called the Dobeshi's wavelet. There's no intuition looking at these things. You look at it and go, what? That? Really? But all these are is just, let's construct something with a bunch of really nice mathematical properties. Who cares what it looks like? You look at it later and you go, whoa, that's crazy. Why would, it's so non-intuitive, yet it satisfies all these amazing mathematical properties, and then it does a great job for you in doing multi-resolution analysis. So we'll talk about that on Friday. All right. Have a good day.